In this example, we are given with this one, a triangular block that is 8" as its height and 6" as its base, and is subjected to a 600-pound vertical load and 1,600-pound horizontal load. And our goal here is to find the normal and tangential components of the given forces, the 600 and 1,600. So what are these normal and tangential forces? So when we say normal, it refers to the perpendicular force component of the load. So let's say that's 600 pound. Its perpendicular component is this one, since it is normal to this surface, right? The line of action of the force is going to be 90 degrees with respect to the surface. Alright? So that's the normal component, while its tangential component is this one. That's going to be parallel to the surface, and so that's why it's called tangential. So this is the surface and that's parallel. Now, before we solve this problem, I'm gonna share to you first the angles. What you should remember when you're dealing with inclined plane surfaces like this one, so that as we go on, you're gonna master this one. So if we have an inclined surface somewhat like this one, and we drop a line, a vertical line, just like this one, as long as that's vertical line, and draw another line that is perpendicular to the surface of the incline, so this line here, so these two are perpendicular to each other, so this is 90, and write that. You need to remember that the angle of inclination of this box is going to be equal to this and this. Alright? Why is this important? It is important because whenever you already had that angle right there, you're gonna easily get what's this and what's this. Alright? So now let's prove why are these equal to each other. Why are this angle equal to this? The perpendicular line and the vertical line created, and to this. It started by the fact that two parallel lines traversed by another line like that. The interior angles are equal. This one, this are equal, so they are vertical. These lines are that traverse each other forms a vertical angle. So no matter what is the orientation, as long as it traverses each other, these angles are gonna be equal to each other. So that's the first idea. So now, since this theta, focus on this triangle right here. Since this is a right triangle, this should be 90 right here, and this should be theta. Then the angle left here should be 90 minus theta. Alright? That should be 90 minus theta, because the sum of interior angles is equal to 180. So if this is theta, this is 90, then what's gonna left would be 90 minus theta, right? So if we write that, 180 is equal to theta plus this angle, let's say that's the unknown angle, plus 90. So if we transpose this, it will become 180 minus 90, and this one minus theta is equal to the unknown angle, and thus 90 minus theta is this angle right here. Alright? Now, focus again on this, another right triangle formed due to this perpendicular line, right? So if this is 90 minus theta, and this whole is 90, this one, this whole triangle is 90, then this should be theta. That's the only explanation. So 90 must be equal to 90 minus theta plus the unknown. So this is the unknown angle right there, unknown angle. If we transpose that angle, these two, it will become 90 minus 90, then this will become positive, so plus theta is equal to the unknown. So it will cancel out, then theta is equal to the unknown angle right here. So that's how you find the angles when you are given with this configuration. You have a perpendicular line, this one, and a completely vertical line touching this surface right here. So whatever the angle of inclination, this and this must be equal to each other. So just a quick start when you have that. If you have a load, for example, somewhat like that, just draw a line that is perpendicular to the surface, and this line, that the line of action of the force, you can quickly say these two are equal to each other. And just like that. And going back to our problem, given problem right here, if we apply that idea to our example, if this is theta, then let's draw another line, this one, perpendicular line, right here. And this, you can see, is the vertical line due to the line of action of this 600 pound force. And we can say that this is equal to theta. And with that, reconstructing our triangle, or the force 600 pound and its components, we can get this one. This is the tangential, and this is the normal. Let's make it bigger, like that. And this angle right here is the angle theta. Now, what is angle theta? It's easy to know what's angle theta because we're given with the sides, alright? So what is the trigonometric identity or trigonometric relation we can use to find theta? It is tangent. So if we take tangent of theta right here, that's opposite over adjacent. So it's gonna be tangent of theta is equal to 8 over 6. And taking the inverse tangent, tan inverse of both sides, this side and this side, we'll get tan inverse 8 over 6, or 53.13 degrees. So now that we know what's theta, that's 53.13 degrees, we can now solve for this one, the normal and tangential, by realizing that this again forms a right triangle. Alright, that's a right triangle right there, because you can see the components of the 600 pound are perpendicular to each other, or forms somewhat like that, right? So by taking the sine of our angle, sine theta, so that's opposite over hypotenuse. So sine of theta is equal to t, which is the opposite, over the hypotenuse 600. And we know that theta is 53.13. And so by rearranging, the tangential force is equal to 600 sine 53.13. And now we've solved the tangential component of the 600 pound force. Alright. Now how about its normal component, this one? So that is adjacent to our angle theta. So we're just gonna use cosine theta. T over 600. N, normal. And so n is equal to 600 cosine theta. That's it. We've done with this first force, right? By plugging this to our calculator, we got our tangential as 480 pounds and our normal as 360 pounds. Alright? So right here, its normal is, the tangential is 480 pounds. And its normal is 600 pounds. 360 pounds. So if you take the square of this one, added to the square of this one, and take the square root, or in other words, the resultant of that, we should get 600 pounds. Because that's the components. Now, moving on to our next force, which is the horizontal one, right here. We should realize that whenever two parallel lines are cut by a transversal, these two alternate interior angles, must be equal to each other. So with that in mind, this, if that's theta, then this should also be theta. We can also prove that by saying that the line of action of the force a while ago, we said that to be this one as theta, right? So this forms a right triangle. So this should be 90 minus theta. Alright? And then again another right angle right here. Alright? 90 minus theta and this unknown. And these two should be equal to 90. So x plus 90 minus theta. This x right here just refer to this unknown theta, and we're just proving it that this is theta also. So x plus 90 minus theta must be 90. So as you can see, x is equal to 90, this one minus 90, and then plus theta. Hence, indeed, x is equal to theta. This angle is equal to that angle. Right? Or again, just realize that these two lines are parallel to each other. Then it's this one. Alternate interior angles must be equal. So now that we have that, we're gonna reconstruct our force and write its normal and tangential component. So this is tangential and normal. This one right here, right, that. And these two is similar. They are similar. Alright. And now that we have that, we know that theta is 53.13. And we can now solve for this one. This is 1,600, I guess. 1,600. And so again, just follow the steps earlier. So t is equal to 1,600 sine theta, and n is equal to 1,600 is adjacent, so cosine theta. So t is equal to, and n is equal to, this is equal to 1 to 80 pounds. So n should be 960 pounds. So now we're done with the problem. So in summary, this is our 1,600, and this is our 600-pound force, and the normal and tangential components are this one. This is 1 to 80, and this is 960, and for the 600, this is 360 and 480 pounds. So this right here is the answer of our problem. Thank you so much for watching, and I hope you got something here. Peace out.